Hello and welcome to this video in which I am going to introduce you to the vector equation of a straight line. In your previous work you have described the straight line as an ordered set of points x, y that satisfy the equation y is equal to mx plus c. The gradient m gives the direction of the line and it is measured as a change of y with respect to x. Unfortunately, this concept of the gradient cannot be used to describe the direction of a line in 3 dimensions. For example, the flight path of an aeroplane must be described using the x and y axes, which are found on the horizontal ground, and the z axis imagined to be vertically above the ground. So we make use of vectors to describe the straight line that the plane follows. For simplicity, in this tutorial we will focus on the vector equation of a 2D line, and we will extend this idea to 3D in a later tutorial. Now let's consider a general point P which moves freely along this line. If we can find an accurate way of using vectors to pinpoint its location as it moves, then we would have found the vector equation of this line. Suppose that we also know a specific point A whose position vector is given as OA, and that the position vector of the point P is given as OP. If we can find a vector which is parallel to this line, then we can use a series or a combination of this vector OA and the parallel vector to track the movement of the point P as it moves along this original line. I have chosen this purple vector to be a vector which is parallel to the original line. You can see that the two are parallel because if I do that they will coincide. Now if I park this vector here, I'm saying that to get to the point P I can use a combination of the vector O to A plus a series of steps of this purple vector to end up at the point P. Now let's see how many of these vectors I'll require to move from A to eventually get to point P. Now you can see if I start there it's going to be 1, and then it's going to be equal to 2 lots of that purple vector. We can actually use algebra to calculate the position of P. Let me call that vector R. Let me call it R1. It's going to be equal to the vector O to A plus 2 lots of the purple vector. But we can actually work out what the purple vector is equal to. As a column vector it's going to be equal to 1, 2, 2 across, so it's 2 and minus 1. And the vector OA is minus 3, 3, so R1 is going to be equal to minus 3, 3 plus 2 lots of the purple vector, which we've worked out to be equal to 2, negative 1. Now if we do that we will end up with minus 3 plus 4, 3 minus 2, and we will obtain the position of P to be equal to 1, 1, and you can see that it is 1, 1 here. So the vector OP is going to be equal to 1, 1, and we can find that vector by using the series of steps. So that displacement is the same as going directly from the origin to the point P. Can we use the same argument to find the location of P if it's now here? Alright, so if I call the new position of P R2, if it's that vector there, I'm still going to go from O to A, so O to A is minus 3, 3 plus, now let's see how many of this purple vector we are going to need to eventually get to P. So that's going to be 1, 2, 3, 4 lots of that purple vector, so it's going to be plus 4 multiplied by 2, negative 1. That's what the purple vector was, and you can simplify this to show that it's minus 3 plus 8, and here is the y component. It'll be 3 minus 4. and you can see that this is going to give us 5, -1, and that on the diagram is the position vector of O to P. It is interesting to note that the vector, this parallel vector which we use to take us from the point A to point P, is not unique. I could have used for instance this other vector here to take me from A to P. How many steps of that one? It's going to be 1, and it is going to be equal to 2. So that vector is not unique. As long as it is parallel to my original line, it can be used. Let's see if this new vector here will end up, we will end up at the same location of P. Now if I denote that vector as R2, because we're still going to that same position, it is going to be from O to A, which is -3, 3, plus we found that it's going to be 2 lots of this now, longer, but it's still parallel to the original line. Now what is this vector going to be? Along the x-axis it's 1, 2, 3, 4. So 4 along the x-axis, and how many along the y-axis? It's going to be 1, 2. So it's be -2. Simplifying this will give us -3 plus 8, and it will be 3 minus 4. And you can see again that it gives us 5, -1 as before. So this vector here that takes us from A to P is known as the direction vector of this line. This shows that this direction vector is not unique. Any vector that is parallel to the original line can be used. It's also interesting to note that this point P could move past A in this direction here. We can still use this purple vector to arrive at the point P. So a combination of O to A plus this vector here should still take me to this location here. Alright, but you have to take into account now that we are going in the opposite direction of the original vector. So what we will need to do is minus this vector from O to A. So the new position of point P, I'm going to call it R3. So if that is R3, then that from O to A is going to be equal to -3, 3 minus my parallel vector, minus because I'm opposing the direction of the original vector, and it's 2, -1, so it'll be 2, -1. And this is going to simplify to -3 minus 2, and that is going to be 3 minus -1, so it'll be +1. And you will notice that this, for the x component, it's going to be -5, and the y component is going to be equal to 4. And you can see on the diagram the coordinates of P are -5 and 4. You must be now wondering how we find a vector which is actually parallel to this given line. Let me just return this point P to here. Now, for me to be able to find a vector which is parallel to this line, I'm going to need to know at least 2 points on that line. So let's suppose that we have another point B that we know, which is positioned there, and its position vector is going to be given by that blue line. Now, if I denote the vector OB by the blue line, a vector which is parallel to the original line is going to be given by the vector AB. I think you'll agree with me on that one. So the vector AB is going to be equal to OB minus the vector OA. Now if I denote this vector OB using the lowercase b, it will be minus this vector A. Now this vector here is going to be parallel to my original black line. So then that vector is our direction vector. So this direction vector could be equal to this one or that other purple one. Now if I use the vector OP, the general location of OP is given by this vector R. It's now going to be equal to some vector OA, which we are calling lowercase a, plus a series of steps of this direction vector. Now let me choose some constant t to represent the number of steps that I'm taking of the vector b minus a. Now this statement here is known as, the statement here is your vector equation of a straight line. Okay, so to put what we have discussed into practice, I'd like us to try this question here. It says to find the vector equation of a line through 3, 7 and 5, 4. If I call this vector here OB, so as a solution, if I call this vector here OB and give it as a column vector 3, 7, and then if I call this one OA, it's going to be equal to 5, 4 as a column vector, then a vector which is parallel to the line that joins the 2 points B and A is going to be equal to AB. So if I take the vector AB to be that, so it's going to be the vector OB 3, 7 minus the vector OA, which is going to be equal to 5, 4, and this is going to give us minus 2, and 7 minus 4 is equal to 3. So this vector here, negative 2, 3, is parallel to the line that we started off with. So this here is our direction vector. Now the equation is going to be given by the location of the point P along that line, and we agreed that we're going to use the vector R to show that position, and I can use any of these two position vectors. I'm going to choose this one, so it's going to be equal to 3, 7 plus a series of steps, which we are going to use T, multiplied by the direction vector, which is equal to minus 2, 3. So this here is going to be the vector equation of my straight line. Please take note, is a real number, and we saw in this example here that it can be a real number 2 or 4. Alright, so this is how we find the vector equation of a straight line. Now to conclude the tutorial, let us find the vector equation of this line here, whose Cartesian equation is given as x plus 3y is equal to 7. And so the task is to find the vector equation of this line here. So this is our second example here. So clearly the equation takes the form r is equal to some vector a plus t multiplied by b minus a. So we are looking to find the direction vector, and we are looking to find some point which lies on the line. Now if I rearrange this here, remember this is the direction vector of the line, so if I rearrange my original equation to y is equal to minus x over 3 plus 7 over 3, the gradient, which gives the direction of this line, is going to be equal to minus a third. Alright, now this gradient as a vector is going to be given as, remember, it's a change in y over change in x, so the direction vector b minus a in this case can be written as minus 3, 1. And now what remains then is for me to find a point which lies on the line. Y is equal to 0. You can see that plugging y is equal to 0 there, x is going to be equal to 7. So I could call this point OA. So OA, or the coordinates of A, will give me the vector 7, 0. So the vector equation of this line here is going to be equal to 7, 0 plus t multiplied by the direction vector, which is minus 3, 1. I trust that this example gives us an idea of how to convert a Cartesian equation to a vector equation of the same line. Thank you for watching. We'll see you in the next tutorial. Cheers.